Good day, students. In this clip, we're going to be going over part 4 on modeling and optimization. In this part, we're going to be looking at minimizing the distance from a point to a curve. So let's go over the steps again, just as a quick refresher. First of all, we're going to model the situation. To generate a model, you need an optimization function, a constraint function, as long as a well-labeled diagram. Part 2, you're going to substitute. You isolate the variable from the constraint and substitute it into the function that's to be optimized. You also state the domain on the constraints of the independent variable you have as your resultant equation. In part 3, you're going to find the potential extremas, which include the critical points and the endpoints if the interval is closed. If it's an open interval, you do not need to consider the endpoints when finding the potential extremas. And you're going to classify the extremas in step 4. And in step 5, you're going to state the meaning of your result. Okay? All right, let's go ahead and take a look at the example. Number 4, it says, what points on the graph of the function y equals 3 minus x squared is closest to the point 0, 2. Also states the minimum distance. All right, so let's start with part 1, where we're to create a model. All right, so to accomplish this, what I'm going to do is I'm going to try and sketch the graph of the situation, sketch the curve, and the point. So we have our y-axis, that's my x-axis. So we have this curve right here. What transformation does this curve apply to the standard y equals x squared function? You have positive 3 and minus x squared. So if you have a standard parabola facing up, plus 3 basically means you're going to shift 3 units up, and then this minus in front of the x squared means you're going to reflect the parabola downwards. Okay? So we have a standard parabola centered at the origin. We're going to shift 3 units up, 1, 2, 3. That will be our vertex. And instead of opening up, our parabola will open downwards. Okay? So let's graph the points. Have a set of points here. Then 1, 2, 3. Then go over here. Our parabola will open downwards. All right, and then the next point goes here, so 1, 2. All right, this is just a sketch of the situation, okay? So let's go ahead and graph the parabola facing downwards. It's going to look something like this. And then we have the other piece through those 2 points. Let's do that again. All right. So with these 2 parabolas, with this parabola, we have a point that we are calculating the distance, we're minimizing the distance from this curve to that point. So the point is 0, 2, so we're 0, 2, we have 0, 2 right here, that's the point 0, 2. Okay? So what we're doing is we're going to pick any arbitrary point. Let's see, let's call the point xy. So if you pick a point here, call that point xy. And what we're doing is we're minimizing the distance from that point to the point 0, 2. So we're trying to minimize that distance, okay? So what we're going to do is we're going to call that distance d. So the length of this segment right here is going to be d. All right, so what is the distance formula? The distance formula, using analytic geometry, remember, d equals the square root of x2 minus x1 quantity square plus y2 minus y1 quantity square. Okay, the entire thing rooted. So this is your distance formula that we're going to be using here. All right, so let's take a look at the optimization function first. Optimization. Optimization, we are optimizing a length or distance. Okay, let's call it distance. Since we're going to be using distance formula, that's what we are optimizing. We're looking for the minimum distance. All right, so in order to use the distance formula, we need 2 points. Okay, so we're going to minimize distance Distance from where to where? Distance from the point 0 to and or to any point xy on the curve. Okay, so all right, so now what we're going to do is determine what x1 and y1 are and x2 and y2. Okay, so the first point is x1, first point, yeah, x1, y1. The second point, x2, y2. So if we substitute these values into our distance formula, that will give us the optimization function. All right, so d equals the square root. Let me use a ruler here since it's going to be a long expression. X2 minus x1. X2 is x minus x1 is 0 square, following this formula, plus y2 is y minus y1 is 2 quantity square. Okay, so that is the expression that we are optimizing. We're minimizing this distance right here. We also need another function or set of functions known as the constraint function. All right, so to find the constraints, we're optimizing subject to a constraint. What is our constraint here? We're constrained by a curve. Okay, the curve that we're constrained by is the curve y equals 3 minus x squared. So we have a constraint and optimization functions. Now let's shift to part 2 of the problem solving process, where we're going to make a substitution. So substitute. If you notice, our distance function is in terms of two variables, which is hard to differentiate in one dimension. So we need to make a substitution here. So what kind of substitution can we make so that this distance function can be expressed in terms of one variable? You see this constraint, that's the beauty of the constraint function. Y equals 3 minus x squared. So let's substitute that into our distance formula. So we have distance equals the square root of x minus 0 is x squared plus, I'm going to change colors here. Instead of y, I'm going to put 3 minus x squared. That is from my constraint function, minus 2 quantity squared. Okay, let's simplify this before we talk about the domain. All right, so to simplify this, this is going to be equal to the square root of x squared plus, and then if you minus 3 minus 2 is 1, so 1 minus x squared squared, and then when you expand that, you follow it out, you're going to have x squared plus 1 minus 2x squared plus x to the 4th. Okay, so the distance formula we're going to be working with, the distance function that we're going to be working with here, that we simplify everything, we're going to have x to the 4th minus x squared plus 1. So what are the constraints on our domain? Let's look at our domain. If you look at this function, what is the domain of x? What are the acceptable inputs for x? The answer is all real numbers. There are no constraints on x. Okay, every input for an x value will have a defined output. So our domain, we have no restrictions on our domain. So the domain for this problem, domain is from negative infinity to infinity. Okay, so that's that. All right, let's look for our potential extremas in part 3. All right, part 3, potential extremas. Potential extrema. All right, so we know that our potential extremas are the critical points and endpoints. In this problem, our domain is an open interval, so our endpoints are not included here, okay, since we do not have any endpoints. So our potential extremas in this problem are basically our critical points, okay? So how do we find the critical points? We find critical points. Critical points are when the derivative, we're dealing with d, that's our function this time. So where d prime is equal to 0 or d prime does not exist. Okay? So these are the two values of x that we are going to be solving for. So let's start by writing down what our distance function is. Our distance function d is the square root of x to the fourth minus x squared plus 1. So let's differentiate this. Remember the differentiation shortcut for radicals. d dx of the square root of x is equal to 1 over 2 root x. Okay? So we're going to apply that here. We also have to apply the chain rule here since we have an input function. Okay, so let's differentiate. D prime equals 1 over 2, differentiating the parent function and holding the inner fourth power polynomial fixed, times the derivative of the input function, which is x to the fourth minus x squared. If we differentiate that, we'll have 4x to the third minus 2x. Okay, so our derivative is 4x to the third minus 2x divided by the square root of actually we have a 2 on the outside, so 2 times the square root of x to the fourth minus x squared plus 1. Alright, so to find our critical points, let's start with when d prime is equal to 0. When d prime is equal to 0, we can just focus on the numerator. Set the numerator to 0, okay, because when you cross multiply, the denominator drops off. Alright, so now let's solve this. We're going to factor, we can factor out the GCF here, which is 2x, so factor out 2x. And then we have 2x squared minus 1 equals 0. Alright, so we're going to set the two factors equal to 0. So we have 2x, set 2x equal to 0, and 2x squared minus 1 equal to 0. Alright, so if we solve this, we end up with x equals 0. And then if you solve this, you end up with x equals plus or minus root 2 over 2. Alright, so these are the points where the first derivative is equal to 0. How about when d prime does not exist? To find this out, what we're going to do is basically set the denominator equal to 0 and solve for that. So 2 times the square root of x to the fourth minus x squared plus 1 equals 0. If you divide both sides by 2 and square it, you're going to end up with x to the fourth minus x squared plus 1 equals 0. This is a fourth degree polynomial. We can easily convert this into a second degree polynomial by making a nice substitution. How about we say let u equals x to the second power. If we make that substitution, we're going to have the quadratic u squared minus u plus 1 equals 0. We can solve this using the quadratic formula, where a is 1, b is negative 1, and c is 1. So if we do that, we're going to have u equals plus or minus, we're going to do negative b, which is positive 1. So positive 1 plus or minus the square root of b squared, which is 1, minus 4ac. 4 times 1 is just 4, divided by 2a. Okay? So that gives us 1 plus or minus the square root of negative 3 over 2. Now, if you examine this term right here, the radical component, you notice is negative. So our solutions here are going to be non-real. Okay, they're not real solutions, not points we can graph on the graph. Points we can graph on the graph. All right, so you know what that means. There are no real values of x that satisfy the non-existence of the derivative. So when is the derivative 0? The answer, when is the derivative non-existent? The answer is never. Okay? So this has no solution. So now we know what our potential extremas are. Potential extremas. Potential extremas in order are negative root 2 over 2, 0, and root 2 over 2. Okay, now next what we're going to do is we're going to classify them. There are two ways we can do this, part 4, which is classify. We can use the first derivative by looking at when the function is increasing and decreasing around the critical points. And if it's increasing and then decreasing, then we know we have a max. If it's decreasing then increasing, we have a min. Okay? Or we can use a quicker method, which is the second derivative. All right? So if it's concave up, we know we have a min. If it's concave down, we have a max. So I like to use the second derivative because it's faster. All right, so we know that all right, so the derivative d prime is equal to 4x to the third minus 2x, that divided by 2 times the square root of, again, the square root of the fourth degree polynomial, square root of x to the fourth minus x squared plus 1. Okay, now let's look at this. I was thinking about using the second derivative test here, but to differentiate this using the quotient rule with all the radical is going to be a mess. So I think let's use the first derivative test. I think that will be much easier to handle. Okay, so what we're going to do here is let's make up our number line and then create intervals that we're going to test. Okay, so that will give us the definitive answers that we're looking for. So our critical points are negative root 2 over 2 is approximately negative 0.7. You can check that with your calculator. And then we have 0. And then we have positive root 2. These are the potential extremas that we have, okay? And then this is approximately 0.7. Okay, so we wanna look for the minimums, okay? We could have one or more, so that's what we're looking for. Now, for interval 1, we're going to let's test x equals negative 1. For interval 2, let's test x equals negative 1/2. For interval 3, let's test x equals 1/2. And then for interval 4, let's test x equals 1. Okay? All right, so we're going to evaluate the first derivative at these points, and then see where it's increasing, decreasing, and then know where our max and mins are. Okay? So let's start with interval 1, x equals negative 1. Now, if you look at this function, the derivative, all we care about is the sign. Okay? The denominator has a square root. Can a square root expression ever yield a negative output? The answer is absolutely not. So since the denominator can never be negative, we just focus our attention on the numerator. Okay? So let's evaluate the numerator. It's going to be 4 times negative 1. The sign of the numerator tells us the sign of the entire expression. Okay, 4 times 2 times negative 1. If you evaluate that, you have negative 4 plus 2, which is negative. So it's negative on interval 1. The first derivative is negative, which tells us something about the function, that it's decreasing, right? Interval 2, we're going to test x equals negative 1/2. 4 times negative 1/2, just looking at the numerator because that's what tells us the sign, times 2 times negative 1/2. That's going to give us negative 4 over 2, which is negative 2. And then if you multiply this together, it's going to be slight mistake here. Let me make a real quick correction. This is supposed to be to the third power. The 1/2 is to the third power. So if we raise negative 1/2 to the third power, we're going to have negative 1/8. Multiply that by 4. We're going to have negative 4 over 8. Negative 4 over 8 and then if you multiply these two minuses, you have plus 1. Okay, so negative 4 by 8 is negative 1/2, plus 1 is positive 1/2, so it's going to be positive. Positive on interval 2, the first derivative. Alright, so what's the sign of the first derivative on the third interval, where x is equal to positive 1/2? Well, let's evaluate the numerator again, because that is what tells us the sign of the derivative. Okay, so 4 times 1/2 to the third power minus 2 times 1/2. Okay, so in this case, we're going to have um, 4 over 8. It's positive this time. 4 over 8, and then times minus 1. Okay, so this is 1/2 minus 1. Our answer is going to be negative. Alright, so it's negative on the third interval. Now let's examine the last interval, interval 4, where x is equal to 1. Okay, so we have 4 times 1 for the third, minus 2 times 1. So we basically have 4 minus 2, which is positive. Alright, so it's positive on interval 4. So it's positive right here. Okay, so what is happening in what interval? We can clearly see that the function is decreasing on interval 1 and decreasing on interval 3. Okay, and the function is increasing on interval 2 and increasing on interval 4. So what does that tell us about the extrema? We have, since it's decreasing and increasing here, this is a min. Since it's increasing and decreasing here, this is a max, relative max. And since it's decreasing and increasing here, this is another relative min. Okay, so we have 2 relative minimas in this function. Okay, so those are the values that are where our minimum distance are. Okay, so which one will give us a smaller distance out of the 2? Well, we actually have to compute what the distance is for those 2 values. Alright, so before we determine which of the distances are is the smallest, or even if they're equally small, let's write down what we can decipher from this chart right here. We have a relative max at x equals 0, and we have 2 relative mins, relative min at x equals negative root 2 over 2 and root 2 over 2. So the question is, which yields a smaller distance, or maybe they're both equally small. So to determine what the minimum distance is, we're going to evaluate the function d. We know what the d function is equal to the square root of x to the 4th minus x squared plus 1. Now if you take a look at it, what happens when you input these two into this function? You're going to get exactly the same output, because these 2 variables are raised to the even power, so the negativity is of no consequence. Okay, so what I'm saying in essence is d of, let's change that to parentheses, so d of negative root 2 over 2 is going to be exactly the same thing as d of root 2 over 2, because where we are plugging them into, they're going to be raised to the second power, to an even power, which nullifies the negativity. Alright, so let's plug it in, since we're going to get the same thing. It's going to be the square root of 2 over 2 raised to the 4th power minus the square root of 2 over 2 raised to the 2nd power plus 1. Okay? Now, if you do the calculations, you're going to have the first term, root 2 to the 4th power is 2 times 2, which is 4. 2 to the 4th power, 16, minus root 2 squared is 2 over 4, plus, we can express this as 4 over 4. Okay, 1 is the same thing as 4 over 4. 4 minus, and then we have to, let's simplify this a little bit more. We're going to have, okay, we can divide the 4 over 16 we can reduce that to 1/4. So we have 1/4, and then evaluate these two, we have plus 2/4, which equals the square root of 3/4, which is root 3/2. Okay, so that's the minimum distance. All right, so what are the points? We know the x-coordinate of our points, but we also need the y-coordinates of our points, right? So when remember the question asked for the points that are the minimum distance to 0, 2. We know what the distance is, but we actually have to figure out what the points are. So when, let's put this for a minute. So when x is equal to the first value, when x is negative root 2/2, what is y? Well, we know the constraint function tells us what y is, right? So y is equal to the 3 minus x squared, all right? And then, so if we plug in this value, we're going to have 3 minus negative square root of 2/2 squared. Okay, so that's going to become 3 minus, if you square root of 2, you have 2/4. Okay, and then we can express this as 12/4. 12/4 minus 2 is 10/4, which reduces to 5/2. Okay, and then when x is equal to the square root of 2/2, we're going to have the same answer, right? Because we're squaring the term, so it's going to be 3 minus the square root of 2/2 squared, which is going to be 3 minus 2/4, which is also 5/2. Okay? All right, so now we're ready to write our conclusion. All right, so conclusion, which is part 5. The minimum distance from the point from 0, 2 on the graph y is equal to 3 minus x squared is, what did we find the minimum distance is being asked? This was the minimum distance when we inputted the x value into the distance function, right? So the minimum distance is root 3/2. Minimum distance is root 3/2, and we also asked for the points, and the points are x, the first one was negative root 2/2, and the y value was the alpha we got, which is 5/2, and the second point was root 2/2, and the y value was 5/2. Okay, so that's that. So thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel for other cool clips such as this. And please post a comment to let me know what you think about this presentation. I appreciate it. More clips can be found on mygosserve.com. Thanks again for watching, and have a wonderful day.